We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, Crash Test Dummies. What is the grisly past behind the development of car safety? Lasers. How can a beam of light blow up a ship? We find out. The sofa. What do horses have in common with building sofas? We take you behind the manufacture of this indispensable piece of furniture. We reveal the surprising science and amazing manufacture behind these wicked inventions. Crash test dummies have become a vital tool in the car manufacturing process, giving manufacturers the ability to test their new vehicles in a variety of crash scenarios in order to ensure that their cars can be as safe as possible. But how did these dummies come about in the first place, and what was the role of a human corpse?
Cars have been one of the most revolutionary inventions of the past couple of centuries, but along with this revolutionary invention, we've had to think about safety concerns as well.
It may not surprise you to know that the history of a crash test dummy begins with the first ever recorded automobile accident. In 1889, an amateur scientist named Mary Ward fell under the wheel of an experimental steam car that had been built by her cousins. 30 years later, an American man named Henry Bliss became the first motor vehicle fatality in the Americas while stepping from a streetcar in New York. Since then, a tragic 20 million people have been victims of motor vehicle accidents, making research into safety crucial. This is where our trusty crash test dummy steps in. As automobiles became a common part of daily life around the 1930s, the death rates rose. There was a total of 16 fatalities for every 100 million vehicles, and this was continuing to rise, meaning that something had to be done fast. Human cadavers, otherwise known as corpses, were used before dummies in the 1930s. Although it may sound gruesome, these were the best option at the time that didn't put anybody's life in danger. In 1949, Sierra Sam was created by Samuel W. Alderson. This first dummy was created to test aircraft ejection seats and can be seen as the first dummy of its kind. Not long after this, an improved version was created that could be used in motor vehicle testing and was produced specifically for General Motors and Ford.
Crash test dummies have helped us to understand the different injuries that we can incur in a car. And indeed, we're always changing the type of vehicles, they're becoming faster, lighter materials, and we still always have to know about how technology is developing and if we can improve safety within those technologies.
It's fair to say that we've come a long way from using corpses, and car manufacturers are now better equipped than ever to provide the safest journey possible for their customers. But how are these amazing dummies actually made? The production of modern-day crash test dummies involve a wide range of materials and manufacturing techniques to create an accurate and reliable dummy that can provide car manufacturers and safety testers with all of the necessary results and information.
Well, Humanetics is the worldwide leader in sophisticated crash test dummies and related equipment. In the automotive sector, we deliver to literally 100% of every automotive OEM in the world.
These dummies are made of a combination of 30 different rubber compounds, 10 vinyl compounds, aluminium, foams, steel, bronze, and specialized metals such as titanium, to name just a few.
So the crash test dummies are very complex, and as a result of that, there's a lot of materials that go into the development of those. So the average crash test dummy that's a standardized product, we could do in about 8 weeks. However, more sophisticated products, newer products that are integrated with more instrumentation and data acquisition systems could take as long as 35 or 40 years.
So, how are they all combined to create a dummy? It all begins with machining. Using a combination of CNC machines and spinning lathes, each of these processes are used to form the metal pieces of the product into the correct shapes.
So in our machine manufacturing, we machine multiple types of metals. We also machine to tight tolerances, anything from thousandths to tenths of thousandths. With that requires a variety of machinery. We have a 5-axis milling machine that holds a tighter tolerance than our old hand mill machines do. So based on the product, determines what cell they're going to be machined in.
These metal parts are used for a wide range of purposes, such as bone structures and supports for the dummy. Sometimes these metal parts need to be permanently connected. In these cases, the pieces are welded together. Now we have our solid metal pieces ready. It's on to the material prep stage, where the rubber is moulded, and then left until it is solidified into its shape. Once the rubber has set, it is released from its mould and any excess material is trimmed off and smoothed. The vinyl parts are moulded next. Raw vinyl is taken and poured into the moulds of the body parts that are needed. These moulds have been preheated in order to get the vinyl piece to form correctly. The freshly poured mould is rested before the excess vinyl is released. The mould is then placed into an oven and left to cure. It's a bit like making some kind of bizarre cake. From here, the mould is taken to foaming, where the spaces in between the sections of vinyl are filled with a special expanding foam. Just like the rubber parts, the now fully formed vinyl body part goes to trimming, where the excess material is removed. That's the vinyl parts complete, ready to join the rubber in the assembly area. Each separate body part is first assembled individually. This is where the metal and moulded parts of our dummy will meet for the first time. These parts are then put together to create the full-size dummy.
Well, because the crash test dummies are very sophisticated, this isn't a mannequin, this isn't something you're going to find at Macy's or a retail store. Every part is anatomically correct. There's biofidelic considerations throughout the dummy. So each arm or leg is going to be correctly sized, proportioned to weight. And the technology that goes into these dummies are very sophisticated.
And with that, our dummy is complete and ready to be moved out onto the all-important testing stage. During component testing, the tensile strengths and range of motion tests are carried out. These tests are undertaken on individual parts rather than on the whole dummy in order to clearly see whether or not everything is working as it should. Full dummy tests are also carried out though. Tests such as the pendulum test, ouch, will test the dummy to see that it is measuring all data correctly. Once the dummy has passed its tests, it is once again broken down and boxed up, ready to provide vital testing and information that will hopefully go on to save millions of lives.
Yeah, this product is absolutely critical for car manufacturers.
Crash test dummies surely are a wicked, life-saving invention. From concert lights to cutting through metal, lasers have become a familiar part of life, leaping from science fiction films into the useful beams of light we use today. But what exactly are they? The name laser is a pretty apt description as it describes exactly what they are. Laser stands for light amplification by stimulated emission of radiation.
What it means is that we take a material, light comes into it, and then it's amplified, and then the light is sent out in a coherent manner, which means that the light is all facing one direction and all in the same path. So that it's all the same colour and it's all essentially one wavelength of light and enough power so you can see the bright light at the end. Now, it doesn't actually have to be in the visible spectrum. We can have ultraviolet, we can have microwave lasers, we can have lots of different types.
Although we regard lasers as relatively modern, they have actually been with us for over 50 years, and the theory behind lasers is even older, with Einstein explaining their theoretical science all the way back in 1917. As with many inventions, the development of lasers had many contributors, but the Russian scientists Nikolai Basov and Alexander Prokhorov are credited with developing the method optical lasers use in 1955. They had come up with laser pumping, which means allowing light to bounce back and forth inside a cavity of mirrors until the light has reached sufficient energy and is released out of one end. The method relies on the behaviour of electrons inside an atom. Electrons orbit the nucleus of an atom. Under normal conditions, this orbit is called their ground state. When they absorb energy, one or more electrons are kicked out farther from the nucleus into higher energy levels. We say the atom is now excited. This excited atom is now unstable and quickly tries to get back to its stable ground state. so it gives off the excess energy it originally gained as a photon of energy in the form of a packet of light. In a typical red laser design, a synthetic ruby crystal is surrounded by a flash tube, which is powered by a high voltage electrical supply that causes the tube to flash on and off rapidly. This provides the initial energy that excites the electrons. But how does the light get amplified?
If you put the same amount of energy in and got the same amount of energy out, it wouldn't be useful. What happens is these electrons drop down energy levels and light comes off. If the light hits another atom that's still in an excited state, so the electron's still high up and hasn't dropped down, it can then knock off that electron and generate 2 photons so far. And then the process can repeat. So you can use a few light photons and each of those will start to amplify because each will hit a few more and cascade the rest of them down. So you actually then start to generate lots and lots of light bouncing back and forth inside the cavity. They bounce back and forth and then they've reached enough energy to punch through the final mirror and produce a coherent beam of light. And so you now have a laser.
The uniformity and controllability of a laser beam means they can be used for many different practical purposes, from fibre optics to eye surgery. Perhaps one of the most familiar uses for a laser is in barcode scanning, which has been used in our shops since the 1970s. Barcodes work by the black and white areas of the code representing numbers, which are based partly on the position and also on the thickness of the lines. As you move a code in front of a scanner, multiple lasers wink in and out of these black and white areas, and a detector translates this information back into the numbers. This combination of numbers correspond with information held in a computer database about the product, such as price, name, and size, which are displayed on the till as the product is scanned. The ability of lasers to read information is not just limited to shops. In your own home, lasers are used to play music and films from compact discs and DVDs.
In DVD players, the light is shone at the DVD and it records the depth or the change that happens when you have a DVD, because there's actually etched into a DVD depth of holes which represent ones and zeros, which represent data for your movie, your game, or whatever else is on that particular DVD.
As a laser beam travels at a consistent speed, they are also used for measuring distances by firing a narrow laser pulse at a point and measuring how quickly it returns. The ability to focus an intense beam of light can also be used for destructive uses. In medicine, lasers can be used to make pinpoint accurate incisions by burning away tissue without causing damage to the surrounding areas. This burning power can also be used by industry to cut materials as tough as metal.
A laser can cut through metal primarily because there's lots of the light going to a very, very small concentrated area, and that essentially imparts a transfer of energy. The transfer of energy is what then causes the material to break down. If it's metal, it'll break down by potentially melting, or depending on the material, it might oxidize in the air and thus give off a vapor, a metal vapor, air, which is a metal oxide in the air. And as that does that, that causes structural deformity, and you can then consider that a cut. It depends on how deep you cut into the system.
With a laser's ability to cut through metal, maybe their destructive power means the laser weapons from our favourite sci-fi films are not so far-fetched. The military already uses lasers in a variety of ways, including guidance systems on bombs and missiles. So, will the future battlefield be illuminated by laser fire that we see in the movies?
Lasers are very good as a weapon system because they can allow a small spot to be heated up very, very fast on a material, and thus introduce a partial destruction, which will then lead to the system destroying itself. There's an aircrafts which actually have a laser mounted in the front, but they do require something the size of a jumbo jet in order to store most of the fuel and all of the related weaponry and cooling systems in order to actually get the laser to work. You can also find them on ships, and again, it's just down to the size of the chemical store that is needed to create the laser in the first place.
From buying our groceries to blowing up ships, lasers have become a part of everyday life and are truly a wicked invention. Can we create a laser microscope to test water samples? We're going to need 2 identical cups, a small syringe, a red laser pointer, and 3 water samples: tap water, pond water, and dog water. To begin, we take the syringe and fill it with a sample of the water. Next, we place the syringe so it balances between the two cups, somewhere near a wall or another reflective surface. We push the syringe down gently so that a drop of the water forms at the head of the syringe. Darken the room, and we are ready to go. We take the laser pointer and carefully aim its beam so that it bisects the water droplet and shines a red shadow onto the wall. Ta-da! Not a lot to see there. But we repeat the experiment with the pond water. Now we can see some microbial action with some of the minute organisms that are contained in the water illuminated against the wall. Now for the dog water. The sample is positively teeming with life and not all of it friendly. Remember the tap water? A positively pure drinking sample. The other two, no thanks. When the laser beam hits the water droplet, the droplet acts as a spherical lens, which refracts the light, causing a magnified image to be projected onto the wall, including the microorganisms lurking in the water. Can we create a laser microscope to test water samples? Yes, we can. Wicked challenge smashed. The sofa has been providing seating for centuries, but just how did it get from a simple wooden bench to a comfort luxury? The word sofa is derived from the Arabic word safar, which roughly translates to bench. However, countries like America refer to it as a couch or even a settee.
It developed over a long period of time, but it was largely in the 16th century that development in furniture really started to evolve. It was probably far more in your wealthier households. A lot of poorer families and everyday families would have still had wooden benches and wooden stools. But over time, these developments, they started to infiltrate through different sections of society.
Prior to the 17th century, the majority of European homes were not heavily furnished, and most of the types of furniture found in homes today were in their early stages of development, or did not yet exist.
Even still, a lot of the early sort of 17th into 18th century furniture, it was still not what we would recognise as the sofa that you sort of collapse into at the end of the day. They were much harder, much firmer, and even the arms and the backs would still be made of wood, but furniture makers were still developing and changing. In the 19th century, you get the Industrial Revolution, and this is where things really kick off because you get improvements in the use of springs and also different materials that went into making what we now know as a sofa.
It wasn't until the 20th century that sofas began being mass-produced, but not many could afford them. However, after the Second World War, sofas were made with more space and were bigger than ever before, accommodating large families.
It was much cheaper, much easier to make. The 20th century really saw a revolution in the sofa becoming an everyday piece of furniture for every household.
But how are these wicked inventions made? Whitehead Designs Limited is a company based in Nottinghamshire, England. They have been producing custom-made upholstery here since 1980.
The fact that we use the traditional methods gives us the flexibility to offer a much more of a bespoke service to our customers, so they're not buying off the peg things. Each piece that we make is pretty much unique really to the end customer in their own fabric, to their own sizes.
They make between 20 and 80 pieces of furniture every week, depending on the complexity of the pieces. Coming up, we'll find out the horsey secret that keeps sofas alive. But first, the production of a sofa starts with the frame. The wood is chosen by the interior designer.
Frames are all hardwood, so they're either beech or birch. The difference with us is there's about 30% more timber in our frames than you'll find in most others. So the frame is over-engineered really, and it's built to last.
The frame is assembled using screws, dowel and glue to give extra strength and support. Once assembled, the sofa's frame is kiln dried. This prevents creaking and cracking in the wood when it is put into a centrally heated house. Next, the springs are attached. Coil springs are used to give maximum comfort. Different strength springs are used in the areas that need more support.
There's different gauges across the spring to stabilise the seat, to stop you falling down the edge of the seat. There's separate tension springs that we can put between the coil springs, which soften the seat further.
The sofa frame is then lined up.
Lining up basically consists of the webs being put on the arm and the foams being put on the arm if we're using foam on that particular job.
The fabric is prepared for the sofa frame. Designers will send their custom design to Whitehead and the fabric will be cut to shape.
The fabric will come in, the cutter will get the fabric, he'll cut that out. He can't use templates or patterns to do that because again everything's different, so it's all done by hand and eye, which is an incredibly skilled job.
The fabric is then overlocked and machined. After this, the body of the fabric is sewn together so it can be attached to the sofa frame.
We sew what we call flies, which is hessian, onto that, which we use to attach onto the frame inside. Now that's a really strong material, so it's a good anchor point for the fabric.
The upholsterer will then start the process of upholstering the sofa. First, the frame is lined with felt.
He will line up the frame with felt. Wherever this coil spring sits on the frame, it needs to be lined out to stop it making a noise.
The same person is used to upholster all parts of the sofa to ensure consistency and pattern machining.
We use one guy to upholster each piece from start to finish. You'll find most companies will use a flow line, so one upholsterer will specialise in arms. It will then have the back done, and then someone else will put the seat in. And the problem with doing it that way is you get a different pull of fabric across each piece, and more importantly, if it's a pattern fabric, trying to get the match the same between the two pieces is very difficult.
Whiteheads use a very traditional method to protect the fabric from wear and tear.
The main difference with us and a lot of others is we still use horsehair across the front of the spring, so that's all hand sewn in to the edge of the spring and right the way down the front edge of the sofa. What that does is it isolates the frame and the spring from the face fabric on the front, so it gives you a really robust front edge of the sofa which is going to stand the test of time. Now that process takes a huge amount of time to do, but it really gives you something that's going to last. We would expect our stuff to be reupholstered 3, 4, 5 times within its lifetime. It's not something you're going to replace after 5 years. It's something you're going to keep for 20, 30 more years, and upholstery, the fabric will wear out before the sofa.
Then the body of the fabric is applied to the frame.
We often get people into the showroom here, and for instance, the husband might be quite a bit taller than the wife, so we will often make a chair a bit deeper for the husband and a bit shallower for the wife so that it fits them. It's very much the same as you'd get if you have a suit tailor-made for them. We tailor-make upholstery for the end customer.
The finished sofa is then checked for quality before being carefully delivered and installed in the customer's home. And that's how you make a sofa that will keep you comfortable for years to come. The sofa, we think you agree, is a wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Crash test dummies, lasers, and the sofa. All wicked inventions.